Now we'll continue with what is work done in irreversible case, right?
Correct.
See, in irreversible process, work done is simply external pressure into change in volume.
Right.
Just remember this formula. So P external, it is the external pressure that is applied, and delta V, it is change in volume for the process.
Okay, V2 being the final and
V1 being the initial.
volumes.
That's it. Remember this formula. And now we'll see a new kind of process. Spontaneous process. What is a spontaneous process? See, if we initiate the process, then if the process occurs by itself, then we call it a spontaneous process.
Okay.
Suppose that, see, let us take a flowing river.
Yeah.
We have a hill.
Yeah.
Water will be flowing from high altitude to low altitude, right?
Yeah. By itself, yeah.
By itself. It is a spontaneous process.
Correct.
So in the same way, if a chemical reaction is spontaneous, it occurs by itself.
Yeah.
So A plus B will be spontaneously converted into C plus D.
Correct.
So we call this process as spontaneous process.
Happen by themselves.
Happen by themselves, exactly. Fine. Now we will see a new term, entropy. What is entropy of a system? See, it is a thermodynamic state quantity. It is a measure of randomness or disorderness of molecules of the system. Suppose that we take a solid. We take gas.
Yeah.
In which case are the molecules more random?
Gas.
Gas, exactly. So gas, here we have more entropy, right?
Yeah.
So this system, it is at less entropy.
Correct.
So entropy, it is nothing but randomness of the system or
Right.
disorderness. Fine, right? Suppose that if you are giving heat to the system, in the sense we are giving heat and increasing its internal energy.
Right.
And now the molecules will be, means they'll tend to become more random, right?
Exactly.
The
The
sense-
arrangement at a particular instant would be random.
Exactly.
Yeah.
So in the sense we are increasing entropy of the system.
Correct.
Fine, right? Remember formula for entropy here. Entropy is Q reversible by time.
Correct.
Sorry, temperature.
Yeah.
Fine, right?
Yeah.
In thermodynamics we don't deal with time. Fine. See, entropy, we always talk about change in entropy,
Yeah.
not entropy at a particular point. Since we can't calculate randomness at particular instant, right?
Yeah, yeah.
So we just calculate change in randomness
Change in randomness.
because of addition of Q or heat supplied.
Correct.
Fine, remember this thing. And now coming to one more term, that is Gibbs free energy.
Oh, this sounds important.
Exactly. Since we'll be discussing about Gibbs free energy in electrochemistry, in chemical equilibrium, in kinetics, everywhere. It comes in many places in chemistry.
Correct.
Fine, right? So what is Gibbs free energy? It is maximum work done or useful work done from a reversible reaction at constant temperature and pressure.
Okay.
Right?
Okay.
It is, so Gibbs free energy, G equal to H minus Ts. So G is useful work that can be done.
Okay.
H is enthalpy, we know, right? In the sense total energy. So Ts, we are subtracting it, in the sense we can't use this energy. So this
Right.
energy, it is carried by molecules or some other things.
Exactly.
So we can use only H minus Ts energy to do work.
Or we can remember it this way, that minus Ts implies that you're removing all the random motion energy from the
Exactly.
useful energy.
Exactly.
Yeah.
So useful work equal to total energy minus unavailable energy.
Right.
This gives us Gibbs free energy.
Correct.
Right? So when a system is in equilibrium, change in free energy will be zero.
Yeah.
So if a system is spontaneous, change in free energy will be less than zero.
Correct.
Since a reaction, it always tries to go from lower entropy to higher entropy.
Yeah.
Means high energy to low energy.
So change in Gibbs energy will always be negative.
Negative, right?
Yeah.
Now,
So it's feasible only if the Gibbs energy lowers down.
exactly. Now we will see the difference between delta G and delta G naught. What is this delta G naught? See, suppose if you are calculating free energy at standard temperature and pressure. What is standard temperature and pressure? These are at room conditions, right? 25 degrees centigrade and 1 atmosphere.
Correct.
If you are calculating free energy at standard temperature and pressure, we call it as delta G naught.
Right.
If you are calculating at other temperatures and pressure, we call it as delta G generally. Right. Now there is a correlation between delta G and delta G naught.
Okay.
So delta G equal to delta G naught plus 2.303 RT log Q.
Yeah.
This is for a particular reaction.
Okay.
See, let us take a reaction. AA plus BB gives rise to CC plus DD. Fine, right?
Yeah.
This small a, small b, they represent coefficients in a reaction.
So basically we are finally entering thermochemistry now.
Exactly. Chemical equilibrium part also we are entering here.
Right.
Now see, for this reaction coefficient is concentration of C power C, D power D,
Right.
A. Right.
Yeah.
This one implies concentration. Concentration of C. Right. This is called as reaction coefficient.
Okay.
Reaction quotient. Right. Now for this, see, suppose we want to calculate reaction coefficient at particular temperature.
Yeah.
We can, it will be very difficult for us to calculate at every instant of our reaction, right? So first we'll be calculating at normal temperature and pressure. That is at standard temperature and pressure. That is, we'll be getting delta G naught.
Yeah.
So if you want at particular temperature, then we'll be using this correlation.
Right.
Since we know the reaction coefficient, then we can get delta G
Directly
at the
from
temperature
there.
and pressure. So
Directly
remember this.
put it into the formula and solve.
Exactly. So remember this formula. So previously we talked about first law of thermodynamics and thermodynamics processes, right? Now we'll be dealing with second law of thermodynamics. See, second law of thermodynamics, it states that we can't completely convert heat into work.
Okay.
In the sense, suppose that you are giving heat Q to the system. So entire heat Q cannot be utilized to do work W.
Okay.
So it is not 100% efficient. The system can't be 100% efficient. Simply we can say like this. Fine, right? So here one thing we need to remember is Carnot cycle.
Which is?
Right. Suppose that we are having a source at temperature T2.
Okay.
And we are having an engine.
Yeah.
This engine converts heat into work.
Okay.
Right. And we are having a sink at temperature T1.
Right.
Right. So source will be rejecting heat Q2 and sink will be getting heat Q1. And in the middle, Q2 minus Q1 work will be extracted by the engine.
Okay.
So here efficiency of the system is Q2 minus Q1 by Q2, since we are initially taking Q2 from the source.
Okay.
Right. Finally, how much we are extracting it as work by how much heat did we take initially.
Okay.
This is efficiency of the system.
Correct.
Right. This can also be told as T2 minus T1 by T2.
Right.
So this is efficiency of Carnot engine. Remember this thing. This is important.
A direct formula again.
Fine. Right. So you'll be getting many examples on this formula. We'll solve it later.
Sure.
Now we'll talk about third law of thermodynamics.
Okay.
See, third law of thermodynamics states us that entropy of a perfectly crystalline solid, it will be 0 at absolute 0 temperature. What is absolute 0 temperature? It is 0 Kelvin, exactly.
Yeah.
So entropy of a perfectly crystalline solid equal to 0 at absolute 0 temperature.
Correct.
Or 0 Kelvin, right? So this is third law of thermodynamics. Here just remember one formula, that is entropy correlation.
Right.
S equal to 2.303 Cp log T. Remember this thing.
Okay.
And
what is Cp here?
This is specific heat at constant pressure.
Okay.
See,
And
we know that
log 2 base 10, right?
Exactly.
Okay.
Delta Q equal to delta U plus delta W. We are doing reaction at constant pressure.
Right.
So if we divide it by mass,
Hmm.
that becomes specific for everything, right?
Right.
So
right.
this one will be specific heat.
Okay. Okay.
So in the case of constant pressure, so delta Q by M, we call it as Cp.
Okay.
Fine.
Yeah.
Right. And now let us see what is there in first law of thermodynamics, second law and third law. See, first law, it is basically conservation of energy.
Simply, yeah.
Yeah, it is delta Q equal to delta U plus delta W. And second law, it states that no system is 100% efficient, right?
Correct.
So heat cannot be totally converted into work, or efficiency is not equal to 100% at any time in real cases. And third law, it states that entropy for a perfectly crystalline solid will be 0 at 0 Kelvin.
Okay.
0 Kelvin. In this part, we'll talk about thermochemistry. Fine.
Finally,
Yeah, exactly. So, thermochemistry, as I told before, see, it is about amount of heat evolved or utilized in any chemical reaction.
Okay.
Right? Suppose that heat is released in any chemical reaction. We call it as exothermic process.
Okay. Heat coming out of
Exactly.
the system. Yeah.
So, as I told you before, most of the chemical reactions we do it in open vessels at constant pressure. So
Okay.
at that point we'll be calling it as enthalpy, right?
Yeah.
So we'll be using term H here.
Okay.
So exothermic delta H less than 0.
Okay.
Since heat is coming out of the system,
Correct.
right? And counterpart endothermic process. If heat is going into the system, right? Delta H positive into the system,
Correct.
right? So suppose that we are having any reaction, there heat of reaction is given as delta H of formation of products minus delta H of formation of reactants.
Okay.
So this is heat of any reaction. Remember this formula. Here delta H is delta H of formation of products. Right?
Right.
Remember this thing. And coming to what is heat of formation. Heat of formation, it is amount of heat released or used when 1 mole of substance is formed from its constituent elements.
Okay.
I'll tell you example.
And 1 mole in particular.
1 mole in particular, exactly. Half H2 plus half F2 gives HF gas, and these all are in gaseous states. It is 1 mole of substance to be formed,
Correct.
and from its constituent elements, right? So HF, and constituent elements are hydrogen and fluorine, and 1 mole of product is formed. So this is heat of formation for HF, whatever heat is evolved in this reaction.
Correct.
Right?
Yeah.
Suppose that we want to find heat of formation of CO2. I take carbon in diamond form and oxygen in gaseous form, and now I get CO2, right? Is this heat of formation? No.
It
Why?
is not.
because here it is not formed from its constituent elements, right?
Okay.
For carbon, diamond, it is not in basic state, right?
Yeah, it is not.
So it is not heat of formation.
Okay.
Fine, right? Suppose
So every time you solve a problem, we have to check if the
Yes.
reactants are in their basic form or not.
exactly, it should
Okay.
be in the basic
Then
form.
only you can
and
call it a
only-
heat of formation.
Exactly, and only 1 mole should be formed. Fine, right? Suppose nitrogen gas plus 3H2 hydrogen. We are getting 2 ammonia gas. Is it heat of formation?
Yes.
No, because 2 moles are formed here, right?
Oh yeah, so divided by 2.
Exactly.
Oh.
So these are the mistakes that we usually do while solving problems. So remember these things. So this is not heat of formation, and previous one it is not heat of formation.
So basically what you have to do is, whenever you have n numbers of moles of product, when you're calculating heat of formation, you divide it by n. You divide the reaction's heat of formation
Exactly.
by n.
And one more example finally. CO gas plus half O2 gas gives us CO2 gas. Is the heat evolved here heat of formation? Guess it.
Guess, huh? CO. Is that the basic form?
I'll tell you right. See, come to basic definition. 1 mole of substance formed from its constituent elements.
Oh,
Is
okay,
CO as an
okay.
element? No. Carbon is an element, oxygen is an element. But CO it is a molecule, right?
So constituents is not in the definition. Constituent
Elements is in the definition.
definition.
So get the definition right correctly. Make this sure.
Constituent elements.
Fine, right? So remember these 4 equations. These are the steps where we commit mistakes usually. So
Exactly.
remember these things exactly. Fine. Now, what is heat of combustion? We talked about heat of formation previously. What is
Yeah.
heat of combustion? It is heat released when 1 mole of substance is completely burned in air. Again,
Okay.
we are talking about 1 mole of substance here.
And the same things hold here also.
Exactly. Same thing in the sense, we'll calculate heat of combustion for anything.
Okay.
So, but only 1 mole of substance should be burned.
Okay.
Right?
Yeah.
It can be methane. It can be something C2H6, something else. So, but
Right.
only 1 mole of substance should be burned.
Correct.
Fine, right? CH4 plus 2O2 gives CO2 plus 2H2O. In this case, whatever heat is released, we call it as heat of combustion.
Okay.
Right?
Yes.
And suppose we need to find about heat of neutralization. What is heat of neutralization? What is neutralization? If we mix acid with base, then we get water.
Yeah.
This one we call it as neutralization reaction.
Yeah.
Right. So heat evolved when 1 mole of water is formed because of neutralization reaction.
Okay.
Then we call it as heat of neutralization.
Okay.
Actually, what happened is, in every reaction some heat will be generated or it will be utilized.
Right.
So depending upon the reaction, we call it as heat of formation or combustion or neutralization or whatever it might be.
Okay.
So these are just different names given for that based on the reactions. Right? So HCl plus NaOH. Here water plus NaCl salt is formed. See here, 1 mole of water is formed. So whatever heat is evolved here, that one we call it as heat of neutralization. In the
Right.
same way with heat of solution. Guess it, what can it be?
When 1 mole of solute is completely dissolved.
Exactly. So heat of solution, it is when 1 mole is dissolved. And heat of vaporization, similarly.
So the heat required to completely vaporize the liquid.
Exactly. That is heat of vaporization.
Okay.
So similarly comes with heat of sublimation for completely converting solid to liquid. Sorry, gaseous state. Sublimation is from solid to gaseous state, right?
Yeah.
So this is heat of sublimation.
Right.
So for our reactions, for any chemical reaction, there will be some heat generated or heat utilized.
Exactly.
So depending upon what is occurring in the reaction, we call it as heat of combustion or heat of neutralization or heat of solution or other things.
Okay.
Right. So these are the key points that you need to remember in thermochemistry.
So guys, this has been really informative. Thanks to Sandeep. Now we'll discuss more concepts of thermochemistry and thermodynamics in the problems that we see next.